Welcome everyone to our webinar from extreme floods to devastating droughts, river discharge data from around the world. We'll wait for a few moments here to let people join in, and then we'll go ahead and get started. Okay, welcome everyone, and thank you for joining us today for our webinar from extreme floods to devastating droughts, river discharge data from around the world. My name is Isaac Jones. I'm Product Segment Manager for SonTek Xylem brand, and I'm joined today by our Senior Applications Engineer, Dr. Xue Fan. And in this webinar, we'll be reviewing some case studies of areas that have been affected by some events, of some extreme flooding events and devastating droughts. As the climate has been changing, these events have become more and more intense, and as these events become more intense, it becomes ever more pressing to monitor water accurately and understand the hydrograph so that we can use this data to monitor floods, do flood preparation, model floods and plan for floods, make inundation maps, and also to monitor how little or how much water we have running down our rivers and streams for allocation. And along with that, this is a pressing reminder to us of how interconnected we are as humans. When it comes to managing water, we see how interconnected we all are and that we're all in this together. So with that, I'll step into the webinar and we'll get started. So an overview of what we'll be discussing today. First, we'll talk about two drought case studies, one from South Africa and then one from the Southwest US. Then we'll step into 3 different flood case studies, one from Oregon in the US, and then Eastern Australia, and another from the United Kingdom. Following each one of these case studies, we have a quick field tip that's related to the data collected in these locations. But if you want the ultimate field tip from a very experienced hydrographer, hydrologist, stick around to the end, because we'll have that one at the very end of this program. So why this topic and why now? I think if you signed up for the webinar, you probably know, but if you take a look at the headlines, you'll see that very extreme, devastating droughts are becoming more extreme in the places that regularly experience droughts, and that places that have never really had to contend with water scarcity are now having to carefully monitor their water as they enter drought situations. On the flooding side, probably top of mind for many on this webinar is the most recent news from India and Bangladesh of very severe and catastrophic flooding there that has claimed the lives of too many people and is affecting people's livelihoods. But it's around the world that the headlines show that there are more intense and more frequent flooding events around the world, like with the droughts in places that haven't experienced such flooding in the past, and also some areas that have experienced drought and then floods, which makes situations even more catastrophic. What comes to mind is the droughts in Australia, causing wildfires and then subsequent flooding, and that causes massive erosion and lots of problems, danger. So with that, I'll hand it over to Dr. Xue Fan, and she will step into our first case study, measuring discharge in drought-stricken South Africa.
Great, thanks, Isaac. So as Isaac mentioned, our first case study is going to talk about some data that was collected in the South African region. Now, you've probably seen the headlines recently in the last couple of years. These are just snippets from a National Geographic video And let me just read them to you. So Cape Town is poised to become the first major city in the world to run out of water. So major dams supplying the city are below 13.5% capacity. And residents are reduced to an allowance of 50 liters per day. And day zero, so day zero is referring to that day that Cape Town will actually run out of water. So day zero looms, threatening a reduction to only 25 liters per day. And just for some perspective, here in the US, each American on average uses about 82 gallons of water per day, so that's 372 liters per day. Just to give you some perspective on what 25 liters might feel like for those residents there. So the area of South Africa is quite complex in terms of their water resources. Here we're talking about the Gauteng province, which includes basically the economic capital of South Africa. This includes, the larger towns like Johannesburg and Pretoria. So that's indicated in this kind of cream color that you see on the map. So what we'll be talking about today is a water project that is meant to take water from the Lesotho region that you see outlined in kind of the bottom part of the map there. So it's taking the water from that region up to the Gauteng province. All right, so this water project is called the Lesotho Highlands Water Project. And again, it's meant to transfer water from Lesotho through a tunnel system all the way up to the Gauteng province to the Mead Dam, which is just south of Johannesburg. And so this water is meant to augment the supply in the province. And again, this is the economic heartland of South Africa. And so what we'll be looking at is a gauging station that's along one of these canal systems here. And the map of the canal system is pictured on the right. And we'll be looking at a station that is the second from the top. If you can see my arrow, I'm circling that station here. And it is the last station before we reach this fork in the system, and then this water eventually flows up to the Mead Dam. So at this site, there's a crump structure here, and the measuring capacity here at this location is 110 cubic centimeters per second. So let's look at some of the data and photos from the site. So this site in particular, the Department of Water Affairs in South Africa usually measures with an M9 using our RTK system. And we were lucky enough to be able to use some of their time in terms of testing the RS5, our newest ADCP. And so these pictures are just from various testing projects that they worked on with us when we were doing the RS5 development. So again, this is the site. They use the RS5 with the SonTek RTK as well as the M9 with RTK because RTK was super critical at the gauging sites along this system. Most of these sites were less than 75 meters wide, and the flows range from 20 to 30 cubic centimeters per second. And so for them, the repeatability and reliability of measurements required the RTK system. Now, when you have a flood event, for example, many times you're going to be looking at a moving bed, and what this results in your discharge value is just a low discharge bias. And so in that case, their GNSS or GPS ship track data was critical in terms of the repeatability of the measurement. So as you saw from the previous map, there are several gauging stations along the whole river system. And along the way, there are many large farms that actually use this water for irrigation. And so it's quite a complex system of kind of tracking where the water goes and being able to measure accurately. So this is one of the primary goals here, is to get a very reliable discharge measurement in the region. All right, so let's take a look at some data from this gauging station. This data was taken using the RS5 with the SonTek RTK. And what I've plotted here on the top plot is the boat versus water speed. And you'll see that most of the colors are green. This means that as you're moving your boat across, you're basically matching the water speed or you're less than the water speed, which is something that we're looking to achieve. Now, sometimes it's not possible. Along the edges, you'll see some yellow and orange colors. That just means that you're moving a little bit faster than the water speed. So generally speaking, you want to try to keep yourself in the green section as you're making your measurement. So if you just take a look at some of the features of the site, you'll see that on the bottom, velocity contours, this is the speed. You'll see some more red colors along closer to the right bank. And so we have, some higher velocities along there. And so the instruments like the RS5 were able to really resolve the more complex shapes and contours of the velocity for this type of measurement. And then a quick field tip. Make sure to check your extrapolations. So in RSQ and River Surveyor Live, the default extrapolation will be your power fit, and that's just following the 1.6 power law. So in RSQ, you're able to use Xtrap, which is a USGS extrapolation tool. And this tool automatically chooses an extrapolation to cover your top and your bottom white areas where your ADCP doesn't measure. And so it's always a good idea to just check Xtrap and see what the extrapolation is picked by the automatic tool. So on the left here is our default extrapolation, power, and you'll see that that line doesn't match quite well with the data profile. But then if you use the Xtrap tool, you'll see that the fit actually matches much better. Now in this case, when you chose Xtrap, the final discharge or Q changed by almost 1%, which might not seem like a lot, but if you're tracking lower flows, especially if you're allotting water to various farmers and keeping track of water during a drought situation, even 1% can be important. And we've seen cases where the extrapolation really makes a huge difference in terms of your final discharge, up to 5 or even 10%. So just make sure to check your extrapolations after you take your measurement.
Thank you, Xue. That's a good tip and interesting case study. And just one addition from the new RSQ software, you can launch Xtrap, and then also once you have settled on an extrapolation, you can apply to all the transects. So it saves time going back and forth between programs, and then also going through and entering different extrapolations in your different transects. So with that, I'll talk a little bit about managing drought in the southwest US. So we're going to take a look at an area near Las Vegas, which is part of the Colorado River Basin. So here for perspective is a map showing the Colorado River Basin, which is spread across 7 western states in the US. There's 4 upper basin states and then 3 lower basin states, and the 3 lower basin states include California, Nevada, and Arizona, are the most arid. This water is critical to those regions and has been kind of divvied up based on this Colorado River Compact that was created in 1922, and basically divvies up all of the water that the Colorado River was estimated to be flowing at on an annual rate. So this yearly average was 16.4 million acre feet per year, or 641 CMS over a year. But the actual, so this was based on historic data, but it was actually based on some what turns out to be pretty wet years preceding the compact. The actual annual flow since this compact has been more like 13.2 to 14.3 million acre feet per year. But we continue to divvy up the water based on this original estimate and these allocations that were based on divvying up this initial average. And that's as we enter one of the worst droughts of record. So this is the Western Drought Index. So the more negative, the worse. Obviously, you have the indication on the left of mild, moderate, severe, and extreme, and we're now in 2022 into the extreme territory for for those more arid southwestern states. And just some visuals to kind of help highlight that. This is Lake Mead, which is along the Colorado River at the Hoover Dam. The photo on the left is from 1983 when the reservoir was near capacity. And then the photo on the right-hand side is from 2022, and you can see that the water level has dropped a lot. And this is based on us using more water than what has actually been flowing down the Colorado. So we've been depleting the reservoirs along this river system. So just one more example, kind of from almost the water line, showing the water intakes at the Hoover Dam and near capacity, and then in 2021 where the water level has dropped significantly. One more visualization showing the map view, the overlook view from satellite imagery, and just in the last 21 years, 22 years, how the lake has shrunk in size. And so for our case study here, we will be zooming into an area just to the east of Las Vegas. It's called the Las Vegas Wash, and this it drains the Las Vegas Valley, so stormwater, treated water from Las Vegas, and runoff. It drains all of this eventually into Lake Mead and the Colorado River system. And why look at such a small piece? And this is just to highlight some data that was collected along here for gauging near a USGS gauging station. And this is partially to highlight that like every drop matters, right? So we have allocations for this Colorado River water that it basically, so that it basically runs dry before it enters the Gulf of Mexico like it has in the past. So all of the water is allocated, so every drop counts. So here's some images from the Las Vegas Wash, and here's the data. So this is not a high flow site. It fluctuates daily based on the amount of output from the water treatment center for the Las Vegas Valley. This is RS5 data using the RTK, so it can collect data, very detailed data, the structures of the flow as this is going down, and eventually into the Colorado River system. And so with that, a field tip for this this field tip is you don't forget to calibrate your compass. You must have a valid compass calibration and magnetic declination when using GNSS, also known as GPS. So even if you go to your site and you intend to use the acoustics for the track reference or bottom tracking for the track reference for the boat, if you have a GPS, we recommend you assemble it with the GPS and do a compass calibration. That way you have a backup track or a backup reference if there's something wrong with your bottom tracking. And so one indication that you don't have a good compass calibration is that your tracks would diverge, your bottom track and your GPS track, granted no bottom tracking. One way to take a closer look at this is to look at the GC minus BC in the tabular data. If this is an indication of how much separation you have between your bottom track and your GPS track. If that value is small, then it's okay. With that, I'll hand it back over to Xue for our next case study.
All right, so now we're going to do a 180 and talk about the other extreme, flooding. So let's start with the first case study, the historic 2012 flooding in Salem, Oregon in the US. All right, so during the most recent January 2012 flood event, Salem actually received 9 inches of rain within a 5-day period. Now, in this region in particular, when you have heavy rainfall combined with snow melt, this can cause substantial flooding in this region. And so for this particular flood event, approximately 300 people were evacuated, and 64 city streets were closed due to high water. So these images just show some of the extent of the damage that was experienced during this event. Now, with these events, now this event in particular was actually considered a 100-year event, and we've been hearing more and more frequently. Just a couple weeks ago, we were at the Alert Users Group conference, and we just, we're seeing these 100-year events, 200-year events, 500-year events within the last couple decades even. And so, is this the new normal? Should we recategorize, some of these types of events, and they're no longer as rare as they used to be? All right, so in this case study in particular, again, we're talking about this Salem, Oregon event, and this data and the photos involved are courtesy of Jeff Budnick from the West Consultants. And the measurements that West does for the city of Salem, they basically have a contract to do these flow measurements, especially during these flooding events. And the data are used to adjust their rating curves, and then the rating curves are then used for flood models, floodplain models, inundation models, and that sort of thing. And so this work for the city is really a kind of a preventative measure to, in terms of the early warning systems for floods. So Jeff usually goes through a series of levels when they're actually taking a discharge measurement during a flood event. So they usually start with a moving boat measurement. Now, in a flood event, often you see a pretty high sediment load just from the runoff during the event. And you can see from these photos here, this water is quite turbid, or there's quite a high sediment load here. And so if for whatever reason the sediment load is too high, you're having issues with bottom track for whatever reason, the acoustics are just not penetrating as far as you need for a moving boat measurement, they would then go to a stationary measurement. And just as a reminder, in RSQ, you're able to use both moving boat and stationary, or this is the mean section or midsection method, it's from the same software. So you can use either mode when you're out in the field. And so if stationary fails in this case, then they'll actually go try to look for a new cross section. That's not usually easy to do, especially during a flood event, because you have very limited access to some of these sites. So when all else fails, they might try AA meters, which often work well in higher velocity water. So that's kind of just a level of steps that they take during the flood event. So let's take a look at some of the data from this site in particular that was shown in the photo in the previous slide. So their average discharge values are around 218 cubic meters per second. And I've plotted here the data ship tracks in this middle plot. You can see these little sticks with vectors. Now, if you look at the bottom track, which is the blue line, you'll see that it's pretty different from the purple and the yellow line, which are the GPS-derived tracks. So this usually indicates some sort of moving bed, especially if your bottom track is upstream of your GPS track, or you could have some issues with your bottom track in terms of losing bottom track information. So usually when you have a moving bed, many people will do a moving bed test. And this is, again, available in RSQ. So you've got your loop method or your SMBA moving bed test. In this particular case, there was a loop moving bed test done. And this is the result of it on the right here. And you'll see that there's a warning. Percentage of bad bottom track value exceeds 5, and loop may not be accurate. And so here in this case, you have this obvious bad bottom track when you're doing your loop moving bed test. And so in this case, you don't want to use whatever correction results from your loop method to correct your data here. And in this case, it looks like the GPS tracks are in good shape, and you probably want to go to your GPS track for your ship track here. All right, and a final field tip for this case study: be prepared to measure your shallow banks as well as your deep flows in a flood event. So in most cases, when you think flood, you think, okay, you'll probably take your ADCP out on sort of a boat-mounted system or on a float tethered to a bridge, that sort of thing. But when you have overflow, especially into city streets, like this example here. This is actually Jeff standing in the middle of the street taking a flow tracker measurement. Just make sure to bring your whole arsenal of techniques and systems available so that you can measure the very shallow flows, even weighting measurements, as well as your deep flood measurements. So just something to keep in mind. And with that, I'll hand it over to Isaac for another case study.
Thank you, Xue. And good tip. Not too often we see flow tracker measurements made in the middle of the street, although I've heard of a couple of cases. So now I'll talk about this very recent Eastern Australia flooding that happened just earlier this year, spreading over like the end of February through March and into April. So here's a map of Australia showing total rainfall and then some highlighted areas affected by the flooding. And this is centered on, or this affects Eastern Australia, and we're gonna kind of zoom in on Brisbane, where you can see there's a red circle. So it was affected by flooding, and you can see some other surrounding areas were pretty affected too. And then also highlighted here is some areas received over 900 millimeters of rainfall in just 1 week. So for Brisbane, we're going to zoom in on Brisbane because it's a very populated region and kind of it hit pretty hard by this flooding, and this is where we have a data set from. So in Brisbane, there was 677 millimeters of rain in 3 days in late February. So this was Brisbane's wettest 3 days on record, and the largest 3 and 7 day totals ever recorded in Brisbane, exceeding the 1974 records. There was catastrophic flooding in 1974, and the damage from floods is expected to reach almost 1.5 billion, maybe more by now. I've seen a couple different numbers for that, but this plot on the right is to kind of highlight the intensity of this rainfall event. So the x-axis is the cumulative rainfall, and then the y is the months during the year, and then the blue or the purple area and the top line is a very wet year. The blue line in the middle is kind of medium, and then the bottom is very dry. And then year to date, you see this plotting. 2021, 2022, year to date is way up above the very wet years based on this event, so early in the season. So the impact, 20,000 homes, probably plus now, inundated, flooded, and 51,000 without power for several days. The Xue Dam, which was built just after the 1974 flooding, to both create a reservoir to provide Brisbane with water, but then also provide flood protection, peaked at 184% of capacity. And luckily, it started at about 50 to 60% because that left room to hold back water. There was inflows of 2.2 million megaliters and only released 150,000 megaliters. And it's been said that the flooding that happened in Brisbane would have been much, much worse if this dam wasn't in place and wasn't able to hold back so much water. And I have a quote here from Professor Stuart Kahn, an expert in water management at the University of New South Wales, says that the Xue Dam gained about 1.450 billion liters of water, which came in under 3 days. That's about 3 Sydney harbors worth of water. So to kind of put that in context about how much water was held back by this dam to help lessen the flooding, because there was still catastrophic impact of the flooding. And some more visuals to kind of show the timeline over this flooding event. This is at Glenore Bridge. So this is the first image was before the flooding. This is at the peak of the flood or about the peak, and then after the flooding. So now stepping into the data, this is An M9 measurement, the data shown below is shown by RSQ, is a screenshot from our RSQ software for the RS5, but you can also open and post-process M9 data sets in RSQ, and it's much more flexible, has some additional features. But the water level reached 8 meters, mean velocity of 2 meters per second, and a max velocity of 3.34 meters per second. So that's moving, and this is a lot of water. The discharge was over 5,000, 5,500 cubic meters per second. This flood in such a short time frame kind of went up through the whole hydrograph. So from the very well documented and characterized lower end of the hydrograph up through a big gap in the data, this measurement helped to characterize that hydrograph where there wasn't data, and for the understanding of that hydrograph at this site. This is on the Brisbane River. The tip for this field tip is check for moving bed. So it's kind of intuitive, or if you've been doing this a bit, that like if it's flooding, you're most likely going to have a moving bed, so you should check for a moving bed or use GPS. But I just want to highlight that there's two main tools for use in River Surveyor Live and RSQ for checking for moving bed if you're uncertain. We have the loop method and the stationary moving bed analysis. So both of those are tools to check and see if you have a moving bed. And one of the reasons we check for a moving bed, because if there isn't a moving bed and there's good bottom track, then the preferred track reference is actually your bottom track. There's less assumptions, there's less calculations done, and less possibility for errors if you're using the acoustic bottom track reference for your track. And then your second choice, if there is moving bed, and good GPS, is to use your GGA track reference. And then third option, if there's moving bed and bad GNSS or GPS coverage, then use the stationary method. So as Xue highlighted, the RSQ software for RS5 you can just toggle between the two different methods, and you don't have to switch different softwares. And so you can check with a loop method or a stationary method, and if you do have moving bed, you can move over to referencing your GPS, or just toggle over to the stationary method. With that, I'll hand it back over to Xue to talk about some flooding in the UK.
All right. So this is our final case study, and I just want to give a shout out to Rob Davies, who provided these photos and the data here. So in February of 2020, this event was considered a remarkable month in hydrological terms. So this is actually the fourth wettest month on record since 1910, and it was a result of 3 different storms in the region. And so below on the bottom left here, you see a map of rainfall anomalies over the UK region in February of 2020. And you'll see all these purple colors in the central UK region, and these are all 350% to 400% above average. So we were really hit hard here in the kind of central northern UK regions. Although the whole region, as a whole country, has these blue colors, which indicate around 200% above average. So this was quite a significant event for the entire area here. And so some photos of the damage that was seen. You can see some bridges that were near flooded, and just these great floodplains that were quite widespread. All right, so this in particular, let me go back to the site here. I'm going to be talking about a site that is indicated by this green star on the bottom left plot here. So this is a regular gauging station that these folks go back to normally. And so the normal situation here is on the bottom right, and you see a nice peaceful bridge scene. And during this flood event, this measurement was actually performed You'll see this pink board on the torrent board with an M9 using the DGPS or differential GPS solution. And so you see that the water is almost at the top of the bridge here at this point. Now let's look at some of the data from this event. And on the left here, this is actually a KML export. The RSQ software has the ability to export the actual ship tracks based on GPS. So as long as you have a GPS ship track, you can export to Google Earth and actually plot your ship tracks on a map here. So this is a nice, convenient tool to be able to visualize your data. On the right here, this is just a snapshot of RSQ, and as Isaac mentioned, you are able to use your RSQ software to open M9 and S5 data files, so you can use that in post-processing, which gives you a lot more abilities and functions. So just taking a look at some of the flows that we see here, the measured Q, or measured discharge, is almost 700 CMS, and the maximum speeds that we reached here, about 3.5 meters per second in this case. This very top plot, I have plotted the pitch and the roll. So this red line here, you'll see the pitch is actually exceeding about 10 degrees. It's almost reaching about 15, almost 20 degrees here. And normally what we recommend is for pitch to be under 5 degrees. And now I know that during flooding events, when you have very high velocities, this is near impossible to do. And so especially when you're tethered on a bridge, your boat tends to sort of lift up the front of the boat when you have these higher velocities. So sometimes that's not it's not preventable, but in terms of a field tip, how do we combat excessive pitch and roll? So in the RSQ software, you'll see on the bottom left here this QC QA warning window, and in this data set in particular, you'll see some pitch and roll warning. So this says pitch and roll exceeded calibrated value. So when you're actually doing your compass calibration, you want to make sure that you calibrate to at least the pitch and roll that you're expecting when you actually take your measurement. And this is really to correct for any of heading errors in the compass. So if you exceed the pitch and roll, then you might start getting some heading errors. So that's something, first off, to keep in mind. So just make sure that you calibrate it to the expected pitch and roll that you're going to see. And then in terms of trying to get the front of the boat or the bow of the boat down, there are various techniques that people use that work. Two of them are shown on the right here with these photos, and so there are different types of weights and different types of systems that you can rig up in order to really weigh down the front of the boat, especially during a flood event or high velocity measurements where your boat tends to pop up at the front. Now, when, as I mentioned before, we're looking at 5 degrees pitch or under as the ideal situation. And once we start pitching a lot more than that, these assumptions that we make when we calculate velocity, they actually start to break down. So it's just something to be aware of, and we know that it's not always easy to prevent this, but something that you should consider when you're in the field taking, especially a flooding measurement.
Thank you, Sheila. And so now just to recap some of the featured instruments, some of the instruments that were used to collect these data sets that we've taken a look at. So first off, we have our relatively new River Surveyor RS5. So this is the smallest and lightest complete ADCP. It's a one-piece solution. The batteries and radio are inside the head of the ADCP. And we mentioned quite a few times also the SonTek RTK. So this is the RTK system. It's a fully integrated antennas and receivers and batteries are all one piece that connects. One connects to the RS5, and then the other is for a base station for reference. We also looked at data from the River Surveyor M9. So the RS5 is kind of is specifically designed for smaller channels, shallower channels. Then the M9 is for kind of mid-depth, medium depth, and it's a multi-frequency ADCP that automatically toggles between a couple frequencies and different acoustic methods to get you the best data possible in the slow, shallow bank areas or floodplain areas all the way through the main channel, using just one instrument, measure as much of the data as possible, as much of the channel as possible. And then the flow tracker 2 is a weighting in ADV for measuring discharge using the midsection or mean section methods. So those are some of the instruments that were highlighted, a few of the SonTek instruments. And with that, we're going to wrap it up. And in conclusion, in drought and flood, flow data becomes more and more critical, right? You don't have enough water, so you want to know exactly how much is there so it can be allocated properly, or there's too much water and people's lives and livelihoods are in danger. So safety is a big one for flooding, and then livelihoods and how you grow food and provide water to different places is important on the flooding side. And basically, when it matters most in flood and in drought, when you have too much or too little water, measurements are the most critical, but also can be the most difficult. So these are just a few of the tools that SonTek offers to help make measurements in these type of situations. Because when we're kind of in the middle somewhere where there's enough water, but it's not threatening our banks, we tend to over allocate or and not worry too much about the water flow. So that's wraps up this presentation, and we want to acknowledge the people who helped make this presentation possible by providing some data and some photos and backgrounds on these different case studies. So thank you to Jeff Butnick from West Consultants, Rob Davies in the UK, Pete Wigsell in South Africa with Monitoring and Control Laboratories, and then the South Africa Department of Water Affairs, and from Xylem, Lee Pemble, our application engineer in the UK, and Daniel Wagner, an application engineer based in Australia, and Josh Sutar, also based in Australia. So thank you again to all of you for providing data and images to help make this presentation possible. And as promised, our last field tip, best flood gauging safety advice ever, from a senior or a very seasoned hydrologist. If you feel the bridge start to move, drop the ADCP rope and run. At the end of the day, what's most important is that we all make it home to our families safe and sound, and not that you sacrifice all to make the measurement. So this comes from Steve Gustafson of West Consultants, formerly the USGS. And with that, that concludes our webinar, and we'll now move into answering some questions. All right, so you want to start, Xue? We have a few here.
Yeah. I've got in some questions. Actually, I'm going to give this one to you.
Take that.
So one question, is it possible to use water level measurements to estimate flow rate using LiDAR? Generally speaking, yes, and that's kind of the traditional way that most gauging stations, at least in the U.S., are operated. It's a stage discharge relationship, so a stage discharge rating curve. Now, with flooding events in particular, and this is research that we've been working with Professor Marion Leste on, he's at University of Iowa, and Professor Dong-Soo Kim of Korea. We're seeing that during flood events, this one-to-one stage discharge relationship doesn't always apply. And, this is kind of site-specific, and we're still looking at the data, this kind of widespread data through whatever we can get. And it's really showing that we need more than just a level during a flood event to get an accurate discharge measurement. But that, generally speaking, yes, you can do just water level measurements. But once you get into these more complex situations, especially during a flood event, then you might want to look at something else. Some of the choices are doing an index velocity rating for the site. Some people will look at the slope area method for discharge. So those are the things that we're actually actively investigating and researching.
Yeah, that's a good question. And if I could just add a little something that also once there's velocity indexing, and then there's also developing a stage area discharge rating curve that's not just a simple stage area, or and so that can be characterized using an ADCP up through the different, by making measurements at the different stages and creating a curve and then associating it with a level. So based on the level read from a LiDAR or pressure sensor, you can get a more accurate discharge measurement. The next question I have is, what does AA meter mean? And so what Xue was referring to there is what's called a price AA meter, and it's a mechanical meter with cups that spin around, kind of like a wind anemometer, for measuring water velocity.
Let's see, another question. When do you use NRTK correction, and what is the difference between this RTK and PPK? So I'm assuming NRTK refers to network RTK or NTRIP corrections. This is a good question because we actually have this feature available in the RSQ software. So you're able to either use your network corrections or just our SonTek RTK system. The difference between network RTK and normal RTK is that the network RTK mode doesn't require a base station physically with you. So our normal RTK setup has a rover and a base station. Network RTK assumes that some other agency, whether it's a government agency, private agency, has set up a base station for you already. And you usually sign up for some sort of subscription service to tap into their base station. And in that way, that base station acts like the normal RTK base station that you would normally use. So in terms of network RTK in the field, as long as you have some way to access the base station, usually what we normally use just a hotspot. If you do have cell service, if you have any other type of internet service wherever you're measuring, that will be good for you to tap into the network RTK service. Once you have that, you can just use a rover and take your measurements. You don't have to worry about a base station. But oftentimes this isn't available at specific sites, whether it's because your region hasn't set up a service like this, or your network RTK base station is too far away that you're going to have large enough errors to not make this worthwhile. You will want to have a physical base station, so you have your rover base station pair in order to get your RTK accuracy there.
Yeah, and if I could just add one thing, the network RTK is a great option, but some of the same restrictions or guidelines and assumptions apply as using a base station on the bank of the river with you. Is that you need to have a virtual or like a connection to an actual base station via the network RTK that's close enough to provide accurate corrections too. So if you're in an area that doesn't have nearby network RTK stations, then it might not be an option as well. So thank you, Xue. That was a good question. Next question is, do you make bathymetric maps with the cross-section data, or is the main goal flow-based? And this is a good question. Everything we've talked about here, the RSQ software and the River Surveyor Live software for use with the RS5 and then the M9, those are softwares that the main goal is discharge. That said, you do get, if you have GPS connected, you do get location and depths once per second. So you can map out the bathymetry, you can map out your cross-section using the ADCP for use in stage area discharge rating. And then you can also use multiple cross-sections collected by RSQ or River Surveyor Live to create a bathymetric map by just using the location and depth data. But then we also have the option with the M9, we also have a Hydro Surveyor M9, which can be used with HYPACK surveying software. So you can run the Hydro Surveyor M9, the same hardware, with HiPAC and do an actual bathymetric survey, and at the same time you're collecting water velocity data as well. So that's a good question. And if you're after strictly bathymetric data with flow data being secondary, the hydrosurveyor would be the way to go.
Our connection to the M9 is frequently lost at just over 100 meters. Is this normal? It kind of depends. So there are a couple things that happen in terms of communications with the M9 or with the RS5 too. The line of sight is extremely important, and the frequencies that are used for the communications, if you're using the most recent PCMs that use the 2.4 gigahertz frequency, this frequency is a Bluetooth frequency, so it's pretty heavily attenuated by water. So if you have like yourself in between the antenna on your laptop and the M9, you might see some issues. Sometimes it's helpful to raise the antenna above the water, so the further you are from your actual water, the more reliable communication you get. There is a setting for the M9 in particular. If you go into your utilities software, there's a setting for low, medium, and high radio power. And so if you do notice that for whatever reason you're just not making the distance that you expect, switch it to high power. I know there are some countries and some regions where that high power might be problematic, so just make sure to check your local rules and regulations before you use that. But that's something to try if you're really struggling with communications. And then of course, just make sure all your connections and things, there's no rust or corrosion on any of your connectors to make that intermittent.
And if it seems like everything that Xue just mentioned is okay and you're still getting a restricted range, then I'd recommend you call or email tech support to help you walk through isolating, whether it's the hardware or something else. Another typical source of interference that we don't always think about is we humans are made up of a lot of water. So if you're standing between your PC and the radio antenna and the ADCP, you could be blocking the signal as well. So our next question is, do you have plans to organize training sessions in Europe in the near future? I don't think we have anything planned in terms of like a general training session, but if you email us at inquiry@sontek.com with your request, then we can send your message to Lee Pemble and Nick Martin, our reps and our application engineers and sales people in the UK and that are responsible for Europe to see if we can set something up.
Let's see. Do you have guide tutorials on how to process data? I don't know of anything that we have readily available, especially for RS5 and M9 in particular. But we are hoping to do more sort of live tutorials and video tutorials this year and the next coming year. So if there are any particular things that you want to hear, processing data, there's so many different aspects of it. So if there are specific things that you're looking for, again, just write into inquiry@sontek.com and we'll try to get to those in a timely manner.
Or enter in the chat now too. That works.
Mm-hmm. Yeah.
And let us know what medium would be best for you,
Mm-hmm.
video or
Mm-hmm.
presentation or document.
Yeah.
All right. So let's see. If bottom tracking is bad, can you still measure the velocity profile okay? And I guess that would extend to, can you measure the discharge? And the answer is quite possibly yes. If the bottom tracking is a different acoustic ping, and sometimes it's a lot harder to track the bottom than it is to measure the velocity using the acoustics. There's actually less pings allocated for bottom tracking than for velocity profiling, so it's easier to lose. And then if you have a moving bed, a mobile bed or a kind of liquefied bed, then it can be hard for the acoustics to track your speed over the bottom. So yes, as long as your velocity profile is reaching near the bed, shown in RSQ or River Surveyor Live, then you should be okay.
Question, can you use RS5 software to open M9 data? It didn't work for me. There's a trick to it.
Good question.
Yes. So if you push the Shift key and then click the Open button on your RSQ software, that will indicate to the software to look for your RIV and RIV-R files from your M9. So you should be able to see your M9 files if you just click Shift and then hit the Open button.
Yeah, that's a very good question. And then also to highlight some of the reasons why you might want to do that, there's new features in RSQ to post-process data that were not available in River Surveyor Live. So for instance, you can subsection the transect, so you can chop out like from a certain sample number to a certain sample number and have that as a separate discharge file, or for whatever reason you might want to subsection a data set. We have a few other things in there that are helpful.
All right. This question here: how much sediment can the ADCP handle?
Yeah, that's a good question. Very good question.
The answer is it depends. It really depends on what type of sediment is in the water. So with the acoustic signals, you know, if you have too much sediment, the acoustics just you won't propagate it through the water, and so you're not going to get a return signal and velocity. But vegetation usually tends to absorb the acoustic signal more than like hard grains of sand, for example. So it really depends on what's in your water and the ratios of that sort of thing. So the best thing to try is just stick it in the water and see what you get. It might surprise you the ranges of sediment load that you can measure in.
Yeah, it definitely is very dependent on the concentration and the type, because round sand grains, the acoustics travel through without too much problem, but platy silt and clay particles are very efficient at blocking the acoustic signal. And one quick way to check is, like Xue said, you try it, and the vertical beam on the M9 is a lower frequency, so it should register the bottom, and then if you see your velocity profile is just not extending all the way down, that's a quick way to check.
All right, so I think we're just up on time here, and we're through with questions. I think there are a couple more remaining questions that we'll get to. Just want to remind everyone that you will get a recording and also a document of all the questions and answers. So the questions that we haven't addressed here, you will get them in written form after this webinar. So as long as you're signed up through your email, then you should receive all that material after the fact.
Thank you, Xue. And thank you everyone for taking the time to join us today. Again, if you have additional questions, requests, suggest anything, please email us at inquiry@sontek.com, or if you haven't, put something into the chat today, and look for that recording, send it around to those of your colleagues who might find it helpful or interesting. Thank you all.
All right.